Everything you are doing right now, I mean, staring at a glowing screen, listening to this audio, it is all a massive illusion.
Oh, absolutely.
Right. Because beneath the glass and the metal of your device, there's no actual fluid motion, there are no colorful images, and there is no continuous sound. It is just a relentless, microscopic storm of tiny electrical switches opening and closing billions of times a second.
Billions of times. It's wild to think about.
It really is. So today, our mission is to completely demystify this ultimate black box for you, the computer. We are going to be unpacking a comprehensive stack of technical documentation on fundamental computer architecture. Basically, we want to show you how a machine that literally only understands on and off can somehow render like hyper-realistic 3D graphics, play beautiful symphonies, and perform math so complex it sends rockets to Mars.
Yeah, because we sit in front of these interfaces every single day,
Yeah.
right? And we take that seamless experience completely for granted.
Oh, 100%.
But to understand the trick behind the illusion, we really have to travel from the almost invisible world of individual bits all the way up to the massive orchestration of a modern CPU. And the strangest part of this whole journey is that the foundational blueprint for everything your laptop or phone does today, it wasn't actually created by an engineer or a computer scientist.
Okay, let's unpack this because everything traces back to a 19th century mathematician named George Boole. And the crazy thing is, Boole had zero intention of building a calculating machine.
No, not at all.
He was simply trying to create a mathematical map for human thought. Right. He wanted to distill the logic of how we reason into a strict algebraic system.
Exactly. Because before a machine can calculate a single number or display a single pixel, it needs a framework for how to think in binary. And Boole provided that framework. So we're starting at the absolute bedrock of computing here, Boolean operations. Boole developed a system of logic that manipulated true and false values, rather than numerical values like, 5 or 10. So in the digital world, we map false to a 0 and true to a 1.
Just a binary state.
Right. And from there, you have a set of core logical operations. So you've got A and D, or, XOR, and NOT.
And the source material actually has this beautifully quirky example to make the logic concrete, which I loved. So to understand the A and D operation, imagine the statement, Kermit is a frog and his piggy is an actress.
The classic Muppet logic test.
Exactly. So for that entire compound statement to evaluate as true, both individual parts have to be true. If you feed it one true and one false, the whole thing just crashes down to false.
Yeah, and what's fascinating here is the XOR operation.
Which stands for exclusive OR.
Right, exclusive OR. It works a bit differently. So it only produces a true output, a 1, if the inputs are different from each other.
Oh, okay.
So if one input is true and the other is false, it outputs a 1. But if they are both true or they're both false, it outputs a 0. And the English language doesn't actually have a single conjunction that captures this specific mechanism perfectly. We usually have to stumble through something clunky like either A or B, but absolutely not both.
Yeah, that is clunky.
Right. But in digital logic, however, it is a non-negotiable building block.
Okay, I can see how mapping out logic is great for a university philosophy class, but how does a physical machine actually execute this? I mean, we can't just teach metal and plastic how to reason.
Well, we have to build a physical bridge between abstract logic and engineering, and we do this using components called gates.
Gates?
Yeah, a gate is a physical device built out of microscopic transistors. Think of a transistor as an incredibly tiny electrical valve. By using a small amount of electricity on one wire, you can basically open or close the valve to control a much larger flow of electricity on another wire.
So we map high voltage to the concept of true, or a 1, and then low voltage to false, or a 0.
Exactly, and you route those voltages through a specific arrangement of transistors. A gate takes those input voltages, physically applies one of those Boolean logic rules we just discussed, and spits out a new output voltage.
Right.
But a computer that only reacts in the present moment is, well, it's basically a calculator. To run complex software, the machine has to remember its past states. And we achieve this with something called the flip-flop circuit.
The flip-flop. I genuinely love that the architects of the digital age went with such a playful name for this.
I know, it's great. But it perfectly describes the physical action taking place. A flip-flop is created by feeding the electrical output of one logic gate backward into the input of another gate.
Wait, backward?
Yeah, you are essentially creating an infinite feedback loop. So because the electricity is trapped in this loop, the circuit remembers a 0 or a 1, it holds that electrical state continuously.
Yeah.
Yeah, so send a pulse of voltage to one side, it flips to a 1 and stays there. Send a pulse to the other side, it flocks back to a 0. This tiny looping circuit is the fundamental, irreducible base unit of computer memory.
I'm trying to visualize this. Taking one looping circuit and building a few bytes in memory makes sense. But modern computers have gigabytes, which means, what, billions of these microscopic flip-flops?
Billions, yeah.
So how is that physically manufactured? We aren't building these by hand.
No, definitely not. It requires a process called Very Large-Scale Integration, or VLSI. Engineers aren't sitting there with tiny tweezers wiring these gates together. They use photolithography.
Photolithography.
Right. They essentially use highly focused ultraviolet light to project a microscopic blueprint onto a tiny wafer of silicon. And then they use chemicals to etch millions or even billions of these transistors and logic gates into a single chip simultaneously.
That is incredible. Okay, so we've figured out how to trap a single bit of information in a microscopic silicon loop. But if you want to run an operating system, or like load a massive video game, for instance, you have to wrangle billions of these bits simultaneously. That means we have to figure out where to physically put them all.
Right. Because memory in a computer isn't just a single giant warehouse. It is fiercely specialized based on speed and permanence. You essentially have two main categories. You've got main memory, which you probably know as RAM, and then mass storage.
RAM, right. I've always conceptualized RAM, random access memory, as a stage performer spinning plates on sticks.
That's a good analogy.
Yeah, because the CPU has immediate random access to any plate it wants without having to search down a whole line. It's incredibly fast. But the most common type, dynamic RAM or DRAM, is volatile. Those bits are stored as tiny electric charges that dissipate incredibly fast.
They really do.
So the computer has to frantically run down the line, constantly refreshing that memory by replenishing the electrical charge, dozens of times a second. And if the power drops, all the spinning plates crash instantly.
Which is precisely why pulling the plug on your desktop just completely vaporizes your unsaved document. Because RAM requires so much babysitting and constant power, we rely heavily on mass storage for permanence.
Like hard drives.
Exactly. The classic example is the magnetic hard disk drive. Inside, you have thin spinning platters coated in a magnetic material. And a mechanical read-write head physically hovers over the disk, altering the magnetic polarity of tiny readers to represent ones and zeros.
It's like a microscopic record player.
Very much so. The data is organized in concentric circles called tracks, which are then chopped up into tiny arcs called sectors.
And to squeeze every last drop of efficiency out of that physical space, the source material actually details this trick called zoned bit recording. Because the tracks on the outer edge of a spinning disk are physically much longer in circumference than the ones credited near the center hub, right? So engineers pack significantly more sectors into those outer zones to maximize the storage.
Yeah, it's super clever. But then you see a totally different approach when you look at optical systems like CDs or DVDs. Instead of those concentric circles, a CD relies on one single microscopic continuous spiral track.
One continuous spiral.
Yeah, it starts from the inner hub and spirals all the way out to the outer edge. A highly focused laser reads microscopic pits and lands on the reflective surface as the disk spins.
Okay, here's where it gets really interesting, though. A massive chunk of the audience is listening to this right now on a smartphone or a laptop using a solid-state drive, so flash memory. There are absolutely zero spinning magnets, there are no moving lasers, and no continuous power refreshing those volatile spinning plates we talked about. So how does a tiny flash drive hold on to my photos in a desk drawer for 5 straight years without a battery?
It physically imprisons electrons.
It imprisons them.
Literally. When you write data to flash memory, the device sends a massive spike of voltage that forces electrons to jump through an insulating barrier into microscopic chambers made of silicon dioxide. And once the voltage stops, those electrons are basically caged in that chamber.
Wow.
They can't escape. So because they are physically trapped, they can hold that negative charge for years without any external power source.
But wait, using massive voltage spikes to blast electrons through a microscopic wall? I mean, that sounds violently destructive at an atomic level?
Well, it is. The act of repeatedly forcing electrons in and out physically degrades the silicon dioxide barrier. So every single time you erase and rewrite a file, you are permanently damaging that microscopic cage just a little bit more.
Yikes.
Yeah, eventually the flash memory will fail to hold a charge entirely.
So the device basically has a built-in death clock.
It does. But to combat this, solid-state drives employ sophisticated wear-leveling algorithms. So the controller chip constantly shuffles data around behind the scenes. It moves frequently overwritten files to fresh, less used physical locations on the drive.
Oh, to spread out the damage.
Precisely. It ensures that all the tiny molecular cages wear out at the exact same pace, which drastically extends the total lifespan of the drive.
Okay, so we've built the buckets to hold the voltage, whether it's on a spinning magnetic platter or trapped in a molecular cage. But ones and zeros aren't an email, they aren't a photograph. How do we force the chaotic, rich physical world into these rigid binary boxes?
Well, the translation process starts simply with text. Early computing was honestly a localized mess. Every single manufacturer had their own proprietary way of encoding the alphabet.
Sounds like a nightmare for compatibility.
It was terrible.
Right.
But then the American National Standards Institute stepped in and created ASCII. It was a 7-bit and later 8-bit standard that mapped specific bit patterns to the English alphabet, numbers, and punctuation.
Right.
But ASCII was painfully limited. It completely ignored the vast majority of the world's languages. So the industry eventually solved this by developing Unicode, specifically the UTF-8 standard.
Right, which we still use.
Yeah, by utilizing flexible patterns of up to 21 bits, Unicode allowed computers to flawlessly represent characters from Chinese, Japanese, Hebrew, and thousands of specific symbols. It finally unified global digital communication.
So text is fairly straightforward. You just assign a permanent number to a letter. But translating visual images gets infinitely more complex, doesn't it?
Oh, completely.
Because the standard brute force method is the bitmap. You take an image, chop it up into a massive grid of tiny dots called pixels, and then use binary to describe the specific color of every single square in that grid.
Right, but the fatal flaw of a bitmap is scaling. If you take a tiny, low-resolution photo and try to blow it up to the size of a poster, the computer doesn't invent new detail.
It can't.
No, it just takes those original tiny grid squares and makes them massive, resulting in a chunky, pixelated mess.
Which perfectly explains why graphic designers rely on an alternative, which is geometric structures.
Yeah.
So instead of recording a static grid of dots, the file stores a pure mathematical description of the shapes.
Yes, exactly.
This is the magic behind computer-aided design programs, or even just the TrueType fonts you use every day in a basic word processor. The letter A isn't saved as a picture of an A. It's saved as a collection of mathematical equations dictating the curves, the lines, and the angles.
And because it's fundamentally just math, the computer recalculates the drawing every single time you change the size. So you can scale a TrueType font up to the size of a highway billboard, and the edges will remain razor sharp because the underlying geometric equation scales infinitely.
That's brilliant. Okay, so we've wrangled static letters and static images. But the real world isn't static. A sound wave is a fluid, continuous change of physical pressure in the air. So how do you trap a continuous flowing wave using discrete, rigid ones and zeros?
You use a technique called sampling.
Sampling.
Right. The hardware rapidly measures the amplitude, so the physical height of the sound wave, at incredibly fast intervals. To achieve what we consider standard CD quality audio, the computer slices that wave up and samples it 44,100 times every single second.
That is just incomprehensibly fast.
And for every one of those microscopic slices of time, it records a 16-bit number to capture the exact height of the wave.
The source text has this brilliant analogy to explain why we even bother with all this translation. Like, why not just keep everything analog like old cassette tapes or vinyl? It compares analog and digital systems to measuring water in a bucket.
Ah, right. If we connect this to the bigger picture, it makes so much sense. In an analog system, the signal is continuous. You are trying to measure the exact precise level of the water in that bucket.
Right.
But if the table gets bumped, the water sloshes around. That physical disturbance instantly ruins your exact measurement. And in audio terms, that sloshing is static, hiss, or interference noise.
But a digital system completely changes the rules of the game. Because you aren't trying to measure an exact fluid level anymore, you are simply asking the bucket a yes or no question. Are you basically full or are you basically empty? Are you a 1 or are you a 0? So even if the table gets violently kicked and the water sloshes wildly, it is still incredibly easy to tell if the bucket is full or empty. This massive resistance to physical noise and degradation is the exact reason the entire telecommunications industry, I'm talking television, radio, phones, abandon analog, and sprinted toward digital infrastructure.
Yeah, that pristine digital robustness is wonderful for storing a song or transmitting a show, but the illusion completely cracks the second the computer has to actively calculate something using these rigid binary boxes. This is where the physical limitations force the machine into making massive mistakes.
This is a crucial pivot, because how exactly does a computer do math, and where does it fail?
Well, when a computer does math, it relies on binary addition, so adding columns of ones and zeros. But handling subtraction efficiently requires real engineering genius. Computers use a system called two's complement notation to handle negative numbers.
Okay, two's complement.
The rule is surprisingly simple. If a binary pattern starts with a 1 on the far left, the computer treats it as a negative number.
Wait, I need to understand how that actually functions in practice. We flip the leftmost bit to mean negative, but how does the machine actually crunch the numbers without a dedicated physical subtraction circuit taking up precious space on the silicon?
It acts exactly like a mechanical odometer in an old car rolling backward. Let's use a base 10 analogy. Imagine an odometer maxed out at 99999. If you add 1, it rolls completely over past 0 to 0000, right?
It resets.
In a digital two's complement system, the binary pattern of all ones 11 and 11 represents -1. If you add a positive 1 to it, the binary addition causes the entire register to mechanically roll over to 0.
So you essentially trick the addition circuit into running backward. The computer can perform subtraction by adding a specially formatted negative number using the exact same physical pathways it uses for basic addition. That is so smart.
It's an incredibly elegant physical shortcut, but relying on this rigid physical rollover trick sets a terrifying trap. Because the computer has a hard physical limit on how many bits it can use for a number, you run the risk of overflow.
And overflow isn't just some abstract theory. It destroys systems. The source material highlights this terrifying incident from September 19, 1989.
Oh, this is a crazy story.
Right. A hospital computer system that had run flawlessly for years suddenly completely flatlined. Data was corrupted, the entire system crashed. And the culprit. The software had been quietly counting the individual days since January 1st, 1900. And on that specific September day, the counter hit the value of 32,768.
And that specific number is the absolute breaking point for a 16-bit signed integer.
Exactly. The system used 16 bits. Because it utilized two's complement, the leftmost bit was reserved for the positive or negative sign. That meant the largest positive number the physical memory could hold was 32,767.
Yep.
So when midnight struck and the new day rolled over, the system added 1. But physically, flipping that next bit changed the leftmost 9-bit to a 1. The computer woke up, checked the date, and suddenly believed it was operating in a massive negative timeline.
It's wild.
The entire hospital network catastrophically failed simply because it overflowed its physical memory box.
Overflow is super dramatic, but computers also suffer from a quieter mathematical danger called truncation errors. When dealing with fractions, computers use floating point notation. But because the binary system is fundamentally based on powers of 2, it is physically incapable of perfectly representing certain incredibly common fractions.
It's just like trying to write down 1/3 in decimals.
Yeah.
And you get a 0.333 repeating infinitely. You can never write the exact value.
Exactly the same concept, but binary struggles with different numbers.
Yeah.
So a simple fraction like 1/10 results in an endlessly repeating binary pattern. But the computer doesn't have infinite bits. It hits the end of its memory register and just chops off the rest of the number. It truncates it.
So every single time the computer calculates 1/10, it's slightly microscopically wrong.
Yes. And when a financial program executes millions of calculations in a row, those microscopic truncation errors begin to compound. They grow into massive, highly visible mathematical discrepancies. It happens so reliably that the software engineers who build commercial spreadsheet applications literally write hidden code into the background to artificially round the numbers.
Really?
Yeah, they have to actively cover up the computer's compounding math errors so that uneducated users don't panic when their flawless digital ledger doesn't perfectly balance.
I love that. They literally have to lie to the user to maintain the illusion of a perfect machine. Okay, so we've explored how data is trapped in memory, how the physical world is translated into binary, and how digital math inherently breaks down.
Yeah.
But who is the conductor here? What is actively coordinating this chaotic, microscopic orchestra?
Well, that brings us to the brain of the operation, the central processing unit, or CPU. It basically consists of three primary domains. You have the arithmetic logic unit, which crunches the math and executes those Boolean operations we started with.
Right.
You have the control unit, which acts as the traffic cop routing data. And you have the registers, which are tiny, blisteringly fast-holding cells for the specific data being worked on in that exact millisecond.
And the source points out that the true revolutionary leap in CPU design was the stored program concept. Because before this, if you wanted an early computer like the ENASI to run a different calculation, you couldn't just click an app on a screen.
Oh, no.
You had to physically walk up to the room-sized machine and manually reroute cables on massive plug boards, like an old 1940s telephone operator.
Right, it was extremely tedious. The monumental breakthrough was realizing that the instructions for a program didn't have to be hardwired into the machine's physical structure. The instructions themselves could be translated into ones and zeros and stored in the main memory right alongside the data.
Oh, that makes total sense.
Yeah, so the CPU could simply read its own software instructions and alter its behavior dynamically without a human ever touching a physical wire.
So what does this all mean for how the computer actually runs a program? What did that process look like?
It relies on a relentless, incredibly repetitive three-step rhythm known as the machine cycle. Fetch, decode, execute.
Fetch, decode, execute.
Exactly. First, the CPU reaches into main memory, fetches the next binary instruction, and pulls it into a register. Second, it decodes that instruction, determining exactly which physical circuits need to be energized. And third, it executes the instruction, so maybe it adds two numbers, moves a byte of data to a new location, or jumps to a completely different part of the software. And once the execution is done, it instantly loops back to step one: fetch, decode, execute, over and over again.
And the sheer velocity of that cycle is dictated by the computer's clock. So when you buy a new laptop and the spec sheet boasts a clock speed of, say, 3 gigahertz, it means there is an internal oscillator firing off 3 billion electrical pulses every single second.
Right, it acts as a hyperactive metronome, basically forcing the CPU to perform that fetch, decode, execute rhythm billions of times per second.
And if we look closely at that execute phase, it brings this entire architectural journey full circle back to the very beginning. Right back to George Boole. I want to highlight an incredible practical application of Boole's logic that the CPU uses constantly, called masking.
Masking, yes.
So let's say the CPU is holding a 24-bit string of data, representing a single pixel of color, but the software only needs to extract the 8 bits that represent the red value. How does it surgically isolate just those bits? It uses the Boolean AD operation.
The CPU lines up the pixel data with a mask. And the mask is simply another string of bits where the target section is entirely ones, and the sections you want to delete are entirely zeros.
And because the strict mathematical rule of the AND operation dictates that anything combined with a zero evaluates to zero, the CPU runs the operation across the strings. The blue and green data are violently hit with zeros and instantly wiped out. But the red data is hit with ones, so it passes through the logic gate perfectly untouched.
It's just so elegant.
It is.
Yeah.
Billions of times a second, your CPU is using the abstract philosophical logic of an eccentric 19th century mathematician to physically slice and dice raw data.
You know, if we step back and look at this entire technological stack, it raises a deeply profound question about the future.
Let's hear it.
Well, we started with a pure true-false thought. We built a microscopic physical trap for it using a flip-flop, or caged it in silicon dioxide using voltage spikes. We translated it into a Unicode symbol, and we watched a CPU execute it using a gigahertz metronome. But what becomes painfully clear is that modern computing survives solely on layer upon layer of physical abstraction.
You mean strategically ignoring the reality beneath you to get your job done? Like, software engineers ignore the physical registers. The chip architects building the registers ignore the individual flip-flops. And the electrical engineers designing the flip-flops largely ignore the messy quantum physics of the electrons.
Precisely. They have to ignore the deeper layers or the complexity just becomes paralyzing. But as our devices demand more power, more memory, and thinner profiles, we are rapidly shrinking our components down to the atomic level.
Right.
We are reaching a point where we're using just a handful of individual electrons to represent a single bit of data. We are approaching the absolute physical limits of the universe.
We were quite literally running out of atoms to split. When we hit that physical wall, when it becomes physically impossible to shrink a transistor or trap a smaller number of electrons, what happens to the relentless, exponential pace of technological progress that human society has completely taken for granted? That is a staggering question to wrestle with. The next time you tap your screen to send a text, just take 1 second to look past the glass. Think about the billions of microscopic gates opening and closing, the electrons trapped in tiny atomic cages, and the mind-bending physical architecture required to bring that simple illusion to life. Thank you for joining us on this deep dive. Keep questioning the black boxes around you. We'll see you next time.